Good day, everyone. I am honored to present our research at the International Symposium on Automation and Robotics in Construction 2024. My name is Amr Eldemiry. I'm working as a postdoctoral fellow in the Sustainable Infrastructure Management Systems Lab of the Department of Building and Real Estate, the Hong Kong Polytechnic University. Our paper title is Autonomous Data Acquisition of Ground Penetrating Radar Using LiDAR-based Mobile Robots. We focus on the integration of the ground penetrating radar subsurface mapping with the LiDAR surface mapping technology on a mobile robotics platform. Our presentation will cover 7 sections, starting with an introduction to give you the background. We will then move to the problem statement to clarify what we are solving. Next, we will talk about the robot design and how our robot is built. After that, we will explain the processing framework, detailing how the robot functions. The experiment setup will outline our testing methods. We will follow with the results showing the robot's capabilities. Finally, we will end with conclusion and future work. For the introduction, we want to introduce a surface mapping and subsurface mapping. On the left-hand side, the robotic platform with its 3D LiDAR sensor enables precise mapping and autonomous navigation, which can be used for surface mapping of the surrounding environment to observe all spatial information and generate an accurate 3D model of it. Next, on the right-hand side, the GPR card, which is a key tool for subsurface mapping, uses electromagnetic waves to detect and map what lies beneath. Also, it is crucial for structural health monitoring. These two technologies together can provide us a full spectrum view of our environment, both seen and unseen. Here we will introduce a problem statement. We address the integration challenge, recognizing the need for a unified approach for surface and subsurface mapping. Under accuracy and efficiency, we acknowledge that existing techniques don't meet the required precision and speed, especially in mapping complex terrain and structures. We proposed an autonomous solution introducing an autonomous robot occupied with GPR and LiDAR technologies for thorough and detailed terrain analysis. The solution aims to overcome the limitations of current methods by providing us comprehensive and integrated mapping capabilities. The design of the ground mobile robot for comprehensive mapping is presented here. As shown, the robot consists of chassis, four wheels, a 3D LiDAR sensor, which can provide up to 150-meter range with 3 centimeter range accuracy, and a 31-degree vertical field of view. And also it has 1.6 gigahertz GPR antenna, which provides a depth range of 50 centimeters. Also, the robot has two GNSS receivers for global positioning outdoors. The 3D LiDAR sensor provides high-resolution point cloud data of the surrounding environment, while the GPR antenna enables the detection and localization of buried features. The robot is powered by two batteries that can last for 4 to 6 hours depending on the workload. In conclusion, this robot is an innovative design of a ground mobile robot that can carry a 3D LiDAR sensor and a GPR antenna for comprehensive mapping applications, and it also can work for at least 4 hours. The proposed processing diagram illustrates the steps involved in mapping the surface and subsurface of an environment. The robot is occupied with a 3D LiDAR sensor, a ground-penetrating radar antenna, and also a distance measurement indicator, which is the DMI. The first step is data acquisition, where the robot collects 3D LiDAR and GPR data along with the DMI data that indicates the distance traveled by the robot. The second step is data processing, where the 3D LiDAR data is used to perform simultaneous localization and mapping method to estimate the robot's pose and generate a point cloud representation of the surface. The GPR data is interpreted to produce a subsurface map that shows the condition and the depth of any parent objects. The DMI data is used to align the GPR data with the robot's trajectory. The final step is output integration, where the surface and subsurface maps are combined to provide a comprehensive view of the environment. As shown in this image, the case study was conducted on around 80-meter section of a bridge in Hong Kong. This bridge was suspected of a severe corrosion damage on its steel parts. The bridge was selected based on its age, traffic volume, environmental conditions, and structural design. This bridge was closed for inspection and preparation before the start of the experiment. The GPR robot was deployed on both sides of the bridge at different locations to collect the data. Here we can introduce the surface mapping processing. The 3D point cloud of the bridge as shown in this video is created using the point cloud data obtained from the 3D LiDAR sensor. The point cloud data were processed using the LiDAR SLAM method, which is a technique that spontaneously localizes the robot and map the environment using the LiDAR measurements. Here we can see the sharpness of the final point cloud of the bridge. The robot's trajectory is shown also on the right-hand side, which will be used with the DMI data to align the GPR subsurface mapping. The merged GPR and 3D point cloud data can provide rich information about the environment's surface and subsurface features, such as pipes, wires, and steel bars defects. Finally, in this work, we presented a novel approach for comprehensive mapping using mobile robot occupied with a ground-penetrating radar antenna and a 3D LiDAR sensor. The objective of our study was to evaluate the visibility and performance of this method for detecting buried utilities and creating a 3D subsurface map while mapping the surface features. We designed and built a GPR system that can be mounted on a specially designed trailer that can be towed by the robot. We applied our method to an experimental site with a bridge section where we collected data using GPR and a 3D LiDAR sensor. Our work opens up new possibilities for using GPR as a tool for robot navigation application in various domains such as construction, structural health monitoring, and mining, and so on. Also, thermal imaging is a potential integration to increase the comprehensive mapping information. Thank you very much for your attention.